All right, let's go ahead and get started. So before we go back into our electronic structure and tour and all that, let's talk about our Earth Day projects, since you're going to be doing that in lab next week. So I'll hand out the little. And so if we look at what we're doing, so my idea is that y'all will get to pick kind of a fun demo or something. And so my suggestion would be to work with kind of your lab group, since you'll have lab time next week. And so let's just put that on the calendar. Right, so lab next week is going to be preparing these Earth Day projects. So this is, again, kind of in lieu of our final. So you don't have to take a lab final in here, but we'll just have our project instead. And I put some suggested demos, and so, red cabbage pH, that would just give you like little different colors depending on the pH, and you can make a graphic for that. Slime, acid rain. This morning they had a really good idea of candles, like colored candles based off the flame experiment. But then we'll probably do liquid nitrogen, because I want to do liquid nitrogen ice cream, because that's always a showstopper. So if anybody wants to take ownership of that and help me with that, that's on there. Bath bombs I put as a suggestion. We did that for our science expo, but it's kind of, it needs some work. And yeah, just suggestions. So 5 senses. You could design something to explore, like, eyes, smelling, hearing, taste, and I can have suggestions. You could also do like building molecules with gumdrops or candy or something. And we also have the molecule kits, or like engineering theme, that's fine. We don't have to be strictly chemistry. You could also do like build your own bubbles, like making bubble solution. And so the idea, and what we'll be doing next week in lab, and so you probably want to coordinate with who your potential partners might be. I think I put that 3 students can collaborate. It's okay if we have 4 though, but maybe try to keep it to 3. And so next week in lab, you probably want to bring either a trifold or poster board, and then if people need help, buying materials, just let me know, especially over the weekend. And so here's just an example of what somebody did. And in the past, we kind of did it more earthy themed, but I won't go down the rabbit hole, but I prefer more like sciencey experiments, so that's why I kind of suggested more science experiments. So just make your poster in lab, just give whatever background to the chemistry. I can kind of just leave these out. And again, we had more of an environmental theme, but this shows the red cabbage pH stuff. So this could give you inspiration for that. And again, you don't have to take it to ocean acidification. You could just stick to the pH and talking about that. So that just gives you an idea. So definitely trade numbers and stuff with your groups. And then you probably want to email me and maybe include your group members if you can, of just like what your topic is and if you need supplies. Like if you're doing red cabbage, I can help bring in the red cabbage. Candle people, we already coordinated what like y'all can bring and what I can supply. So that sort of thing. Does that make sense, what we're going to be doing? So just ask me after class if you have questions. And we'll probably take a break between lecture and the quiz, so that'll give you more time to kind of chat with your groups and figure out what you might want to do for next week. So definitely start thinking about it. Send me an email over the weekend or in the next few days if I need to buy stuff for y'all, so that on Monday you're actually able to kind of practice the demo. You know, like if you want to do the red cabbage, you want to practice what that's going to look like so that you can lead our guests through these demos. Because we should have some schools or something joining us. So, all right, questions about the Earth Day project?
When are we going to present them?
So that is going to be, so Earth Day is April 22nd. And so the Earth Day celebration is from 11 a.m. to 2 p.m. And so this is where it kind of depends if you have class or not. So at the very least, we'll present during our class period, right? So since it's during our class, so I'll just put required to attend right from 1 p.m. to 2, since that's our class time. But it would be great if you can come before at 11 and be there the whole time. I know that we'll have our Monday lab, which is kind of, will be chaotic. So what we'll try to do for the Monday lab people is we're still going to try to fit in that next lab before 11 o'clock. So next week we'll do our Earth Day projects. Then week 4, we'll do the lab that's on the syllabus. Again, I think we should be able to squeeze it in for the Monday folks. And then we'll go straight from lab to Earth Day. And of course, you know, you can take a break for lunch or whatever. We will have pizza at Earth Day, so hopefully y'all can eat some food as well. So pizza's always good. And then if you don't have class beforehand and you're not in my Monday lab, feel free to come by anyways. You know, we'd love to have you there the whole time if you can, but I understand if you have class. All right, other questions on that? All right, so let's kind of reorient ourselves. And I feel like we maybe got a little lost with our electronic structure, but we're going to kind of go over it again and kind of start looking at these electrons, and then we'll go back and do our demo as well. So let's just kind of maybe orient more broadly, and then we'll continue on practicing our electron configuration. And so we had started off by mentioning, okay, we have these s orbitals, and so these s orbitals look like spheres. And let's go back to our Bohr model for a second. And so what we started looking at was just this first n equals 1 ring, so just our first energy level. And again, if you might recall from middle school or high school, you learned that it could fill in 2 electrons, so 2 electrons occupy that. So taking our more detailed look, so again, we're starting with our 1s, so that just means our first row. And so that corresponds, again, over here. So this is our 1s as we fill it up. And if we look back at P table, so again, we see the same thing. So we have our electron configuration. So if we hit this button, notice it organizes everything into the S block, P block, D block, and F block. We'll talk about some oddities, though, because I don't quite agree with everything that they have there, but we'll get there when we get there. And so we went over hydrogen, right? So that was 1s1 for 1 electron. And then we filled in helium, so 1s2. And so now we can say a few more things about helium. And so, right, if we notice, this is kind of an interesting choice. So what they're trying to do, they moved helium over here to show that its valence electron is in the s block. And so it's satisfied. But then if we look at kind of our normal periodic table, it's over here with more of our noble gases. And so what I like to say with our helium, again with electron configuration 1s2, so we're saying its first energy level is completely filled up. And so again, we'll get to these. So these are completely satisfied by what we'll call the octet rule. Again, we'll go back and really clarify what that means. Maybe you've heard of this. But we also want to say, well, helium's kind of similar. Helium is also unreactive. It doesn't have a tendency to make a lot of compounds. And so we say that this is satisfied by the duet rule. And so the duet rule only applies to hydrogen and helium, since they're the only ones with the 1s, so that's all they have. So once they have that 1s orbital filled up, they're satisfied. And so again, just kind of review, we did this on Monday, but here's our electron configuration. And again, write this 1 signifying our first energy level, and then our s, so whichever orbital is being filled up, and then total number of electrons. And so right now we're just looking at neutral compounds as well. All right, so then we filled up, so we went from hydrogen to helium, then we did lithium, and so we mentioned lithium, again, had that 2s1, so our valence electron. And then we did beryllium, and so beryllium rounds out our S block. And so now let's figure out where to go from here, because we want to just continue filling in numerically. So the next number would be boron, which takes us to our P block. And so let's step back. And well, what is a P orbital? And so our P orbital, they look like these little dumbbell shapes. And the shading is better if you go like this. So they actually have opposite shading. So here they're just showing more the shape and the space filling model. So this would be more relevant if we talk about orbitals, but that's kind of for other higher level chemistry. And so this is just showing its distribution. So the other thing to understand is, so we don't have to know any quantum mechanics, but we have to appreciate that all this comes from quantum mechanics. And so all this means is that this is a probability density map. So it means, right, that it gives you the probability of finding an electron, and usually these are kind of shaded. And so if we kind of take a closer look and try to understand what I'm saying. So notice how the way they depicted these is it's kind of darker in the center, right, more shading. So this indicates we have a high probability of finding an electron in this area. As we get out to the borders of our orbital, then it's kind of more light and diffuse, so right, we kind of have less of a probability, and then of course it drops off once we get to the end of our orbital there. And so that's all that this is showing. So we have a 0, since there's kind of a node in the center here, so node just means an area where you don't have electrons. And then of course, right, this is going to be your maximum probability along 200 ppms, which I assume corresponds to around here with our high density. And so the other thing to note is, right, we have 3 p orbitals, and each p orbital can hold 2 electrons, so px, py, pz. And so if we go back to our Bohr model, so we want to correlate this. So we have 8, so let's figure out where that 8 comes from. And so at our second energy level, now we have 2 allowed orbitals. So we have either an s and our p. So that's going to be, right, our 2s and our 2p. And so now we can see where the 8 comes from. And so now I'm going to write it in another funny way. So we can write 2p, and these 3 lines represent our 3p orbitals, so I can label them px, py, pz, just for clarity. Doesn't matter who's who. And then 2s, and I put the s lower than the p because normally we're looking at these with some sort of energy on our y-axis, so I put the 2s lower since it's lower in energy. And so other things to note, so if we go back to P table, this helps us give the order of our orbitals, but it also follows along if you fill in order. And so I know like in high school maybe you learn like all those crazy tricks with the diagonal lines and stuff. Do people know what I'm talking about? You haven't seen those patterns. I was talking about this. I don't know if people have ever seen this trick. And it's useful, but it's just more of a memorization versus just learning, well, if we fill in an order, it is the order. And so what I mean by that, and our order is down here. So our 1s is our lowest energy, so it's at the bottom. And so lowest energy means it gets filled up first. So that's why we always, again, start with our 1s. And then notice, right, it goes 2s, and then it's a little hard to tell, but it goes from 2s to 2p. So that's where we are filling this up. And then from there, we'll go to 3s, 3p, etc. So we'll keep going in order. All right, so let's try to write our electron configuration for boron then. So go ahead and try that for a second. So what do we get for our electron configuration? 1s to the 2 and then 2s to the 3. So 2s, so remember we only have 2 electrons in the s, so then we have to put that last one in the p there. And so we can go back to our periodic table. And so we might want to write that if we haven't already. So right now we've left the S block. So again, highlight this as your S block. And then now boron starts our 2p. And then what's also nice to note, so we said how many electrons fit in the p orbitals? So we said there were 3 p orbitals though. So then how many total in the p? So 6. And so notice how many wide this is. So 1, 2, 3, 4, 5, 6. So that matches. And so that kind of makes sense. So let's try the electron configuration for nitrogen and see what we get. So we're skipping carbon. So what do we get for nitrogen's electron configuration? So 2p. So we can just put all the p's together even though there's several of them. And then so let's look at a few other things. So this looks good. And let's again define, so these are our core electrons, and then our valence ones are our outermost, so both of these right on the 2s and the 2p. And we can add them up, so 2 plus 3 is 5, and then that also matches right with our 5 number here, so that tells us we have 5 valence electrons. So that's also good information. And then I'm going to throw one more thing at y'all that, again, we want to start thinking about. So I think this is also chapter 3, if I remember correctly. But we want to practice our Lewis dot structures. And so Lewis dot structures are just another way of kind of showing how many valence electrons. And so you find that, you know, at the beginning of chemistry, these first 2 chapters, it feels like we're just kind of showing how to express how many valence electrons by a bunch of different methods. And these Lewis dot structures are also really powerful. So let's look at this. And so first I'm going to actually write out the energy levels again in the funny order. So we have our 2s on bottom, again, because it's lower in energy, 2p on top. And then I drew all the other p orbitals, right, so px, py, pz. I put them on the same line because I want to show that they are degenerate, which means the same energy level. So all the same energy. And then have you guys ever heard of the Candy rule or Hund's rule in chemistry before? And so, and again, in high school and middle school, sometimes you get an oversimplification of this rule, and I'll kind of show the difference and where you might get some discrepancies. And so usually how it goes is, you know, they say something as everybody gets a candy, and you fill up kind of each side until, you know, all the electrons are paired. And that kind of works for this case, actually. So we do 5, you know, we can do 1, 2, 3, 4, 5, and now we can pair them. And this actually does give you the correct structure. My criticism of this method is that it doesn't take into account that we actually fill up the s orbital first. And so that's kind of the problem, is that we have to fill the s orbital first. And so let's kind of show this on here. So then we start 5 valence electrons still. So 1, 2, and then notice I've drawn the electrons as half arrows. So that's because our electrons can either be formally spin up or spin down, but they can't be the same. So you can never have up and up. That does not exist. So they have to be opposite spins. That's just quantum mechanics. This is the electron, and it's just a half arrow. Because it's a spin up, spin down, because the electrons are formally either plus 1/2 or negative 1/2. And so that goes with like quantum numbers. We don't need to get into all those details in that class. We just need to show that they have opposite spins. And so right, fill in the s orbital first, so 1, 2. Now we can go and continue filling in our p's. But because they're degenerate, we want to put an electron in each orbital before we go ahead and pair them. And so part of that is also you pay an energy price for pairing, so they don't really want to be paired, so you pay a little bit of energy price, but so that's why these are unpaired. So it's more favorable to be unpaired if you can. And then, of course, you have to fill in the next lowest. And so now we can kind of translate these two. And so the way I like to think about it is, well, now we have 4 orbitals, right? 1, 2, 3, 4. And each one of these orbitals, or suborbitals we should say, can represent our sides here and make our Lewis dot structure. And so now, right, we can have our 2s. So, okay, that's represented by these 2 dots, and then our p's on the other 3 sides. And so that being said, it doesn't matter the orientation, so you can draw it, this way, that way. Doesn't really matter. All right, so let's do neon for fun now. So let's do the electron configuration of neon. And so I will say, so right now it's not too cumbersome, but as we continue on, we can start abbreviating our electron configurations, so with our noble gas. And so what that means, and let's just look at neon. Again, it's pretty easy right now. But neon, if we look at the previous noble gas, so that takes us to helium. And that means we can write our electron configuration starting with helium and then continuing on, with the 2s, blah, blah, blah. So I'll let you fill in the rest of that. And it'll probably make more sense as we do more examples. So what do we get for the rest of the electron configuration for neon?
1s to the 2, 2s to the 2, 2p to the 6th.
Yes, so I rewrote it. And so this would be, again, kind of what's called the full electron configuration. Again, right now we're not saving too much ink. Or we could do it the abbreviated. And so instead of writing 1s2, we can write helium, but then we still have to write 2s2, 2p6. But then, of course, going forward, now we can start at neon, like when we do sodium. And so again, just kind of orienting ourselves so we're all on the same page. So there are core electrons again, and then, of course, our valence electrons. And, we have 8 valence electrons. And that's what we expect. So that matches right with our 8 here. And then now we can go back, that's why we have the octet rule. So right now it's completely filled. So that p orbital is completely filled up, along with, of course, the 2s, so giving us the octet rule. And so we can write it, again, in our other forms. So we can write out our 2p, our 2s, fill in our 8 electrons, so 1, 2, 3, 4, 5, 6, 7, 8. And of course I filled it in the proper order dictated by what we call Hund's rule, or just energy levels, filling in the lowest first. We could also write our corresponding Lewis dot structure, and again treating all these like the 4 sides. We have 2 electrons on each side, again showing us why neon is unreactive, right? So again, we have our 8 valence electrons, so octet rule satisfied. So it has filled p and s orbitals, so it's happy, unreactive, so we can say all that.
For the core electrons on the whole configuration, why is it negative? The negative 1s2.
Oh, it's just equals, sorry. All right, so let's continue. And so we were at neon. Now we go down So 10, 11, this starts our 3s. So now we're hinting at, again, our lithium, sodium, potassium reactivity, which we'll see. And so again, important to note that we're back at this NS1, right, for our valence electrons. If we look at our P table, we can see that. So there's our 3s1. But what I also want to show you, and it's kind of hard to see, I don't know if I can make it any bigger. I don't think I can. So if I click on sodium, and then you see over here, we have the little onion rings. And so it's kind of showing you each layer that we're adding. And so let's start back at hydrogen. And so right, again, it had our 1s, and it's just showing the outermost orbital, so our 1s. Then we went down to lithium. And so you can see, right, you still have the 1s, and then theoretically there's a node between the orbitals, so meaning there's a space where there's no electron density. Then your 2s orbital starts, so indicated by blue. Now we're at sodium, so 3s1, and we've added yet another onion ring. And so see if you can write our electron configuration for sodium, but let's use our abbreviated version, so starting with the previous noble gas. So see what you get there. So what do we get for our electron configuration? And you can give me the full shebang if you want to, but otherwise I'm looking for the abbreviated.
So like neon and then 3s to the 1.
Yep, so that's our abbreviated. And so again, all we're saying is beginning with the electron configuration of neon, and then 3s1. And then of course you can write it the full version. So on an exam, I'd probably accept both. I don't think I'd ever ask specifically for one and not accept the other. But again, at this point now we are kind of saving some pen ink, so I'd probably use the abbreviated version. And then sodium, 1 valence electron. So we can write our Lewis dot structure just like a dot. And I'll write, so 3s, I'll just put an electron. And I'm just kind of ignoring the core. Not that they're not there, right? It's just we usually focus on the valence electron, since that's what drives reactivity. And so we're kind of running out of time slowly. So let's go to our demo. So I'll put this on the big screen to help. And so we want to highlight this reactivity. And so I brought with me, so lithium, sodium, and potassium. And so we want to see that, right? So we said, okay, as we go down our group from lithium, sodium, potassium, they get more reactive. And so we want to get into why. And so let's dump the first one in and see what happens. We're going to start with the least reactive, so lithium first. Small piece there, so you can see how big that is. And so you can see it fizzing. If you want to get it closer, you're more than welcome to. So it's fizzing slowly. And so if we add some indicator to this, so notice, right, it's turning pink since it's making our sodium hydroxide. Yeah. Oops. There we go. And so I'm just going to show what reaction we're doing. And so lithium, oh, I have the wrong camera up. Sorry. Working on my high quality video production. So if we add this and we make lithium hydroxide, and then the gas that you see is H2. And so the pink, so I added phenolphthalein, that's just an indicator that tells us that we have base. And so lithium hydroxide, those hydroxide ions are basic. So that's what's giving us our color. So let it keep going. Uh-oh. My problem is my computer is a little finicky. And it starts to smell just a little bit. Sorry. Are you alive? All right, so let's look at the next one. Hopefully it doesn't get too smelly in here. No. Okay, that's good. My camera's not functioning.
It just worked, I saw your name on the
Oh, it did? Okay.
There's just not a lot happening in it up now, or in the extract.
All right, so let's do the next one. So now let's do sodium. Hopefully my camera's working. Oh, okay, good. Sodium.
Sodium's angry.
So nice and reactive. I'll let that finish.
Oh my God, it's on fire.
And so it matches your flame
Ow.
test. I'm just gonna like kind of walk.
Yeah, there's no vents in here.
Yeah, I'm debating whether I should go get the fan from the stock room. Still going. All right, who's ready for potassium now?
Yeah.
And so now we have potassium.
Dump the whole thing in there.
Oh, I'm going to. So potassium does have the danger of auto-igniting in air, which I have had personally happen to me. I'll stop talking while you look at this. Woo! And so that was
That's
nice
awesome.
and reactive. And hopefully you saw the purple flame, which matches your flame test. At least it's not like too smelly. And so, yes, so we saw that. So potassium can auto-ignite in air, so it is the last alkali metal that you're able to work with. And I have had that happen on me. Although the samples that we have in our lab are very old, I think people are scared of potassium. And yeah, so you want to respect the potassium and obviously all the alkali metals. And maybe I'll talk some more stories about that. So they are pretty reactive. And so, right, if you slice a really fresh piece of potassium, sometimes it will just ignite in the air. So that's kind of not scary, but you got to be prepared for it, right? So you should always be prepared for a fire if you're working with something that you know is going to light up. I will say that just as a kind of danger, these things are all sources of good fire hazards. So for example, when I was a young undergrad, we were using some sodium, and I thought I had fully quenched it. So usually the procedure, if you're trying to quench it a little bit, is to add some isopropanol and methanol, and it should kind of fizz. So similar to water, it's just less so. And so I didn't fully quench it though, and there was a tiny piece that I couldn't see. I dumped it into the organic waste and hit it with some acetone, and I lit the entire 20-liter solvent waste on fire. Number one rule of starting a fire is you cut the oxygen, so that's what I did. Is luckily it has those little flaps, so there's like a little collection thing that you pour your solvent in. So I just closed it, cut the oxygen in the fire. Yeah, pretty much. I was pretty freaked out, but yeah, so you have to be careful. So same thing with potassium. You just want to make sure you've cleaned and thoroughly quenched everything. I've seen somebody accidentally light a whole fume hood on fire because they didn't know that the tongs they picked up had residual potassium because someone didn't clean them up. Then they were like, oh, I'm going to clean these really well with some bleach. So they hit the potassium with bleach, which meant whoosh, and it lit the entire fume hood on fire, and that was not a good situation.
And that was the
Well, yeah, this was a research lab, and I happened to be there, so I ran over and helped her stamp out the fire. But that being said, right, we don't want to be afraid of them and like never use them. So that's part of why our potassium looks so bad at RCC is I think people got afraid of potassium. But we shouldn't be afraid of it, just respectful, and it goes just clean and quench everything and make sure it's quenched. So that was fun. And so now let's explain, well, why was potassium the most reactive? Any thoughts on that? And why does it continue to get even more reactive? So I could not bring rubidium in. I've never worked with rubidium personally, but yeah, and so if you want to look at rubidium and cesium explode, I would look at YouTube videos, but it's always just like they're smashing an ampule, and as soon as that ampule breaks, it's reacting. So yeah, don't work with those. But why are they reactive? Why do they continue to be reactive as they go down?
Does the energy level get higher?
So it does have to do with the energy level. So yes, so what happens though as it's getting higher? So what else is going on? And you can kind of look at these pictures, what it's trying to show you. So we went hydrogen, lithium, sodium, potassium. So what's going on as our energy levels increase? So what might you expect happens? So what about the distance of our electron from our nucleus, right? So let's think about that, because that's what's driving our reactivity here. And so now let's put a separate question. So why is potassium more reactive than lithium? And so we want to think about our distance from our nucleus. So of course, right, we have our nucleus in the center. And just a reminder, right, so our nucleus has our protons and neutrons. So that means it's positively charged. And then what happens as our little valence electron gets further and further out, right? So we had lithium is in the 2s, so 2s1 for its configuration. Sodium, right, I'll try to draw. So it's 2s, but now it's 3s1 for its valence electron. And so, right, potassium is even further down as 4s1. So what can we say about our electron and its distance to the nucleus? Yeah, so it's getting farther away. So that's the key, right? So as yeah, so right now we're seeing that. So as we add our energy levels and we add our onion rings, right, that electron gets further and further out, so it's more loosely held. So yeah, by the time we get to potassium, that electron is ready to fly off and react, right, and make potassium hydroxide. So, right, again, you saw how it just lit up pretty much right away. And lithium, right, comparatively, that was kind of almost unexciting. It was just kind of fizzing because that electron is held closer. And so again, as we go down, we get more reactive. And so that's also something that we want to start to write about is our periodic trends. Again, we're just kind of touching on everything, and so you can really understand it, but we'll re-summarize. But we're at least seeing, so radius increases as we go down. That makes sense. So radius increases as we add more onion shells. Okay. I think we'll probably have to stop here just because of time. But we haven't finished our electron configuration. So probably, let's see. So let's do a quick, so you go 3s, and then this is 3p, 4s, and then this is going to start 3d here. But I want to end on that note because I don't want to get into it all. We're kind of running out of time. So just kind of mark that, and like we'll pick this thought up on Monday. And so probably don't stress about electron configurations past like calcium. Maybe y'all can figure out zinc and onward, but I don't want you to get too lost because things get a little funny down here as we continue, and I want to go over it slowly. So we're going to go back on Monday, continue with electron configuration, continue tying it to our Lewis dot structures that we've been seeing, right? So we're going to continue that so we feel really good. And then we'll get into the rest of our periodic trends. All right, so let's take our 10-minute break, and then we'll do our quiz. So during your 10-minute break, other than breaking, make sure you trade numbers with your potential partners for your Earth Day projects so you can talk and text over the weekend and the coming days and coordinate. All right, and I'm going to stop this.